High voltage power distribution systems are essential to the everyday functioning of individuals, companies, and industries around the world. Their transmission lines span over large distances with operational voltages ranging from 11 kV to 400 kV. High voltage systems can cause harm to individuals if not properly managed and need to remain operational in tough environmental conditions. So, how do companies ensure the safety of the public, and how does contamination such as rain disrupt operation? Insulators are a key aspect of uninterrupted power transmission, commonly made out of ceramic, glass, and polymers, in particular silicon rubber. Silicon insulators are becoming increasingly popular due to their low cost, high dielectric strength, and hydrophobic properties, which help to decrease the occurrence of discharges. Discharges are caused by the production of conductive paths of moisture, leading to short-circuiting. This results in mechanical damage that builds up until physical failure and power outages. Hydrophobicity is the ability of a material to repel moisture, which is measured by a contact angle. This is the angle between a droplet of liquid and the material's surface. Hydrophilic surfaces such as PVC, ceramic, and glass are defined by a contact angle smaller than 90 degrees. Hydrophobic surfaces such as silicon rubber have a contact angle greater than 90 degrees. Despite the benefits of hydrophobicity, silicon insulators still suffer from the inevitable surface aging mechanisms, which decrease their ability to perform over time. A potential method to combat this is to apply a superhydrophobic coating, which increases the contact angle beyond 150 degrees, thus delaying the formation of conductive paths for longer than a hydrophobic surface. Such use presents an engineering challenge, as currently no standard exists for the assessment of hydrophobic coatings. In addition, due to their size and placement, applying coatings to live insulators requires careful risk assessments. So how do engineers test the performance of insulators? What equipment is required? And can coatings become commercially viable? Answering these questions was the aim of the project. The first step was to design and fabricate a tracking rig to hold the samples on the top side. This is to encourage the formation of conductive paths. It incorporates an angular motion mechanism to allow the samples to be set at any inclination between 0 and 90 degrees, 45 degrees being the optimal. The second piece of equipment created was a control box, used to monitor leakage current, which triggers a relay to disconnect mains when 20 mA is measured. This box also provides a smoke detector system and various power sources for additional equipment. To aid in the investigation of insulator aging, the following sensors were introduced. These included 2 infrared cameras, a FLIR boson and lepton, to provide live thermal imaging of the tests, a microphone module to monitor auditory activity, and an ultra-high frequency antenna to provide insight into the frequency of discharges. To investigate the performance of the coated insulators, a stepwise voltage tracking test was conducted in 3 stages. Stage 1, the initial testing. Stage 2, conducted 24 hours later, and Stage 3, a week later. Measurements of the contact angle were taken following each test and just before Stage 3. The results from the thermal cameras provided a deeper insight into the formation of conductive paths along the insulator surface, in particular how and when they are formed. It also allowed for observations of how the heat spreads throughout the sample, encouraging discharges to take place, seen as orange bands of light. The UHF and microphone outputs showed linked activity between discharges and leakage current spikes. A benefit of these sensors is that they are non-contact and therefore may be used for in-field testing. Results from the time-till breakdown showed coated silicon lasted for longer periods of time at higher voltages compared to non-coated silicon, which suggests coatings can prolong the lifetime of an insulator. The measurements of contact angles showed variation in hydrophobicity across all 3 stages of testing. Silicon rubber results presented the ability to recover hydrophobicity after the surface had been damaged. Coated silicon, however, does not possess such properties, and in damaged areas a hydrophilic path is created, further accelerating damage. These results gathered with the proposed systems should then be used to influence asset management, which refers to the condition monitoring and evaluation of in-service insulators. For hydrophobic coatings to be commercially viable, appropriate maintenance strategies must be selected, for example, periodic respraying. Future work that could be undertaken includes integrating sensors permanently, implementing a reset button for the control box, streamlining GUIs to run one system, and conducting further testing with different coatings and different environmental conditions.